The topic for this lesson is the diode. The rectifier diode is a single p-n junction device. One half of the diode is a p-type semiconductor and the other half is an n-type semiconductor. The n zone is called the cathode and the p zone is called the anode. The structure and symbol is shown in the illustration. The arrow in the schematic representation points in the direction of conventional current flow. When a voltage source is connected to a diode in the way shown, it is forward biased. The positive terminal is connected to its anode through a resistor. The negative terminal of the source is connected directly to the cathode. The forward current from the anode to the cathode is indicated as I sub F. The forward voltage drop due to the barrier potential is indicated as V sub F. If the negative terminal is connected to the anode and the positive terminal is connected to the cathode, a reverse bias condition exists. The current is zero. The small reverse current is considered negligible. Because no current is flowing, there is no voltage drop across the resistor and the entire bias voltage V sub B appears across the diode. The ideal diode can be modeled as a switch. When forward biased, the diode acts like a switch that is on or closed. When reverse biased, the diode acts like a switch that is open or off. In an ideal diode, the barrier potential, the forward dynamic resistance, and the reverse current are all neglected. The ideal diode operation is indicated in the characteristic curve for the diode shown. During forward bias, since the barrier potential and the forward dynamic resistance is neglected, there is zero voltage across it, or V sub F equals 0 volts. The forward current I sub F is equal to V sub B divided by R. Since the reverse current is neglected, its value can be assumed to be 0, or I sub R, the reverse current, equals 0. The reverse voltage is equal to the bias voltage, or V sub B. When the barrier potential is added to the ideal switch model, we obtain the practical diode model. During forward bias, the diode acts as a closed switch in series with a small voltage, for example 0.7 volts for silicon, which is equal to the barrier. The barrier potential V sub F indicates the voltage drop V sub F across the forward bias p-n junction of the diode. It is not an active source of the voltage. When reverse biased, the diode acts as an open switch, identical to the ideal model. The barrier potential does not affect it. Thus, V sub F equals 0.7 volts for silicon and 0.3 volts for germanium. The forward current I sub F is equal to V sub B minus V sub F divided by R. Since the reverse current is neglected, I sub R is equal to 0, and V sub R is equal to V sub B. When we include the barrier potential, the small dynamic forward resistance R sub D, and the large internal reverse resistance R sub 2, which is considered since it provides a path for the reverse current, we get the complex diode model. In this case, V sub F is equal to 0.7 plus I sub F times R sub D, and I sub F is equal to V sub B minus 0.7 divided by R minus R sub D. Using the circuit diagram shown, determine the forward voltage and the forward current for the diode in the circuit for the three diode models, that is, the ideal model, the practical model, and the complex model. Assume the material in the diode to be silicon. Assume R sub D equals 20 ohms for forward current. For the ideal model, V sub F is equal to 0. I sub F is equal to V sub B divided by R, or 3 milliamps. And the voltage across the resistor is equal to the maximum voltage, or I sub F times R, or 6 volts. For the practical model, V sub F equals 0.7 volts. I sub F is then equal to V sub B minus V sub F divided by R, or 2.65 milliamps. The voltage across the resistor is equal to voltage V sub R is equal to 2.65 milliamps times 2 k ohms, or 5.3 volts. For the complex model, I sub F is equal to V sub B minus 0.7 divided by the quantity R plus R sub D, or minus 2.62 milliamps. V sub F is then equal to 0.7 volts plus I sub F times R sub D, or 752.4 millivolts. The voltage V sub R is then equal to I sub F times R, or 5.24 volts.